Alright, so in this video I have a few more MCQ practice. If you need to pause and read this one. Essentially you have a hanging mass that's released from rest as it falls down. It's going to cause the system to move, and then the pulley here is going to start rotating. Okay. Alright, it wants you to find the angular velocity after this particular hanging mass or weight has dropped a distance h. So let's go ahead and do it. I like to establish my reference point for these types of problems just so I can know what h is. So I drew two lines here. The box starts there and it drops the distance h. I like to take my lowest point to be 0. So here in my work, I'm just going to establish the bottom red dashed line as 0 because that's going to be the lowest point for this particular problem. Well, if that's 0, I like to go upward to where the problem starts, and I'm just going to call that initial position h. Okay, so it's going to go from h to 0. All right. Other than that, I hope you recognize that this is a conservation of energy problem because as you release the box, the force of gravity acting on the box is going to cause it to move downward, which generates a vertical displacement delta y that's in the same direction, that's parallel. So there's work done, and if there's work done, it's going to cause the system to have a change in kinetic energy. Okay, and if there's change in kinetic energy, then there's going to be a change in angular velocity for the wheel itself. So I'm just going to go ahead and start my work with conservation energy here. MEI equals MEF. But initially the wheel wasn't moving, so it has no KE. The block was released from rest, so it has no KE. But it is a distance h above 0, so it has to have some sort of PE due to gravity. So I'm just going to go ahead and expand the left side to equal to PE. After it's released, both objects are now moving. The box though just has a KE linear because it's not rotating. However, KE for the wheel or the pulley here is just KE rod or KE rotational, and it does not have a KE linear, right? It's spinning around its own axis. All right, so on that, I'm just gonna break these terms up into what it's equal to. PE due to gravity is just mgh. KE for the block is simply 1/2 mv. V here is the linear speed square, and then the wheel is just 1/2 I omega square. So again, KE wheel is just the KE rotational. There is no KE linear because it's fixed. On that, I'm just going to go ahead and expand V here. I need to expand V because essentially the question is asking for omega. Here in my statement, I have V that's unknown. I also have omega, so I need to somehow get rid of V. Well, to get rid of V, all you have to do is you really use this bridge function between linear speed and angular speed. Okay, so instead of V, I'm just going to go ahead and substitute that out. V is R omega, so in parentheses here I have R omega. So make sure you have good algebra habits here. Use parentheses when you substitute. And then the exponent 2 here is outside of R and omega, so you need to distribute that to the R and omega. And that really just cleaned up a little bit. So here the only thing different is I just distribute the 2 to the this exponent 2 to the R and to the omega as well. So hence I have R square omega square. Now you have omega square here in the left first term here. You also have an omega left term, excuse me, or right term, and then you have an omega square here also on the second right term. So here, essentially you can combine like terms or do algebra as long as it's correct. It doesn't really matter. It will get you there. But I see there's a 1/2 in this term where I'm going back and forth with my cursor. I also see a 1/2 here. Well, to get rid of the 1/2 here, I can just multiply the whole entire function by 2 because 2 times the half is 1. 2 times the half is 1. So you need to do the whole entire function. So I'm just going to go ahead and multiply everything by 2. If you multiply the left side by 2, you get a 2 mgh. You multiply this 1/2 by 2, it cancels out. You multiply this 1/2 by 2, it also cancels out. So really, I can clean this up. It's just mr square omega square plus I omega square. Okay. But here, again, you have two terms that has an omega square in it. So really, you can just factor out omega square. So really, it's just mr square plus I in parentheses, and omega square is on the outside. Well, the question asks for omega, so at this point, I hope you recognize it's just solve for omega square by dividing both sides by mr square plus I, which I'm going to do, and that's that. And now I know here in my work I have omega square. I haven't really taken the square root yet, right? Because this is omega square. But I think you can just be done here, because really the only difference is you just throw a square root symbol on top, but the function itself doesn't change here. So I'm just going to look for what matches. So here in my numerator I have 2 mgh. So right away I can go to B and C. Both these answer choices have 2 mg and h. On the bottom though, it's mr squared plus I, right? So I need mr squared plus I. Choice B here is just I plus mr squared, which is essentially the same thing. When you're adding, it doesn't really matter the order of the terms. C would not be because the bottom, this term has a 2 next to mr squared, right? So the answer choice here would be B, all right? The next problem is this one. You have a solid cylinder, a circular ring, a solid sphere, and a hollow sphere, and it wants to know which one will reach the ground last. So I think this one's pretty straightforward. If you know your acceleration function, I want to point out that we're looking for the object that reaches the bottom last, meaning it takes the most time, or like if I like to think about it, well, to reach the bottom last, you're accelerating slowest, right? So in this case, I made a point here. You want to look for the shape that has the slowest acceleration. Well, if you accelerate slowest, you're picking up speed at a lesser rate, so it'll take you more time to get to the bottom, which means you're gonna lose. So on that, if you've seen my other videos, the acceleration, the linear acceleration for these types of rolling motion is defined by g sine theta over 1 plus c, where c is your coefficient of moment of inertia for these different shapes. So essentially, I made this statement. Hopefully, if you can read it, I said that if c increases, the denominator increases. So when c gets bigger, the denominator as a whole gets bigger because you're adding. Well, when you divide by a bigger number, your answer comes out smaller. Okay. So in this case, you want to look for the biggest c because you want to look for the object that finishes last, hence the smallest acceleration. So in this case, I just wrote out all the I values for you here. From left to right, this is the solid cylinder, which is 1/2 mr squared. The ring is just simply going to be mr squared, so the coefficient here is 1. The solid sphere is 2/5 mr squared, and then the hollow sphere here is going to be 2/3 mr squared. So just by looking at it, you want the biggest c, right? This is 0.5, half is 0.5. The coefficient for the ring is 1, which is bigger than 0.5. And then this is 2/5, which is 0.4, which is less than 1. And then 2/3 is 0.666, which is less than 1. So in this case, just by looking at it, the one with the biggest coefficient is going to be the circular ring or the hoop here. So you want c to be big, so that's, you know, the one is the biggest coefficient. All right. So other than that, I'm just gonna go ahead and highlight the circular ring as my answer choice for this particular one. Now, what if they ask you which one finishes first? Well, then the opposite is true, right? If you want to finish first, then you want to pick the one with the greatest acceleration. Well, to accelerate greatest, then you need to see that smallest. So you need to be able to, you know, account for the type of questions that's being asked, right? Do you want the first or the last? All right. Other than that, let's move on. So here's the animation to help you visualize this stuff. Okay. All right. So as you can see, the ring in that particular animation there finishes last. So in case you didn't follow, I think it should replay again. There you go. Right, the ring has a coefficient of 1, which means it accelerates slowest, which means it'll reach the ground last. Let's do this one. So here's a conservation of angular momentum problem where you have a disk that's already rotating, and then all of a sudden some object of mass m is going to be dropped on the outer edge, and it wants us to find the angular velocity. So here I'm just going to set up conservation angular momentum. Li is equal to Lf. Initially there's only one object moving, that's just the disk, because the mass here is just being dropped in the vertical direction. So other than that, on the left side, it's just I disk omega I disk, and then on the right side, it says that the mass is stuck to the disk on the outer edge, so it has to have its own moment of inertia, referencing the axis rotation here through the center, and omega f on the outside is the common angular speed once these two objects stick together. Okay. So I'm just going to expand I disk. I disk, once again, the shape of it is just 1/2 mr squared. And then here, instead of omega I disk, the diagram just called it omega. So I'm just going to call it omega. Okay, I'm just going to go with the flow with the diagram here. And then on the right side, I disk is once again is 1/2 mr squared. The moment of inertia for the little mass that's being dropped because it's stuck to the end is just treated as a point mass. So the coefficient is just 1. Well, that would just be mr squared. M being the little mass, the distance away from the axis rotation here is just r, and you got to square that term. Omega f once again just on the outside. So I can see here, you can clean things up a little bit. Okay. Here in my work, I noticed on the right side in parentheses, this is a 1/2. You're adding a whole, so really you need to find common denominator. So what's common denominator? Common denominator is 2. So I'm just going to multiply the second term here in the parentheses by 2/2, because 2/2 is just 1. From here, you can just really clean it up. On the left side, there's a 1/2 on the bottom, or there's a 2 on the bottom. And there's also a 2 on the bottom there. There's also a 2 on the bottom there. So because each of these terms have a 1/2, I'm just going to cancel that out. Okay, and other than that, I'm just going to go ahead and cancel r squared as well. That has an r squared. That one has an r squared. That one has an r squared. So really here, it's just cleaning up algebra work. The only thing left on the left side is m omega. The only thing left in the parentheses here is just capital M plus little m. And there's a 2 on top, so that's 2 times m. Okay, so don't forget about that little 2 on the top there. And omega f once again remains on the outside. So here you're asked to find the angular velocity. So really at this point, just isolate for omega f by dividing both sides by capital M plus 2m, and that's that. So if you look at the answer choices, you need an omega. You need a capital M omega on the top. So let's go ahead and find that. All right. Well, A has an M omega, and then B also has an M omega. C also has an M omega. I would not touch D and E because D has a 2, which doesn't match what we do. And then on the bottom though, you need M plus 2M. So here M plus 2M would match choice A. Okay. This answer choice C says 2 big M. You don't need 2 big M. You need M plus 2 little m. So answer choice is better than answer choice. Answer choice A is better than answer choice C. So make sure you pay attention to the little details there. All right, that's that. And then the last one for this particular video is this one. You have some sort of uniform rod of length L, some mass, and it's released from an angle that touches here the vertical axis. So I like to remind you, always pay attention to where the angle in these types of problems are placed, because it dictates whether you sine, cosine, or so you don't want to be goofing off on sine and cosine, especially when the answer choices are presented with both of these trigonometric functions. All right. So it wants us to find the magnitude of the angular acceleration. Well, to find that, I'm just going to go ahead and set up torque. There are 2 definitions for torque, right? You can find torque by either doing moment of inertia times angular acceleration, or you can do torque simply by taking the force that's perpendicular to the moment of arm. So here I'm just going to set the 2 functions equal, because I recognize that given the system here, well, what's going to cause this rod to fall? Well, the weight, its own weight, right? F of g of this particular rod is going to do that. So I'm just going to go ahead and draw it out here. F of g, I'm just going to place it at the center of mass. So I'm just going to call this F of g, which is big M times g. The problem called the mass of the rod as capital M, so I'm just going to use capital M. All right. Other than that, to do torque, keep in mind that your arm must be perpendicular to this F. Well, F here is placed a distance of L over 2, because it's at the center of the rod, right? Distance-wise. Well, if this is L over 2, you can find what the perpendicular component is super easy, right? So F of g is already in the y direction, so you need the leg that's in the x direction. Well, you can really just do a little triangle here. From the center of mass to the pivot as a distance of L over 2. Therefore, this blue dashed line that I'm tracing back and forth with my cursor, that's the opposite leg. So it'll be L over 2 sine of theta, not cosine, right? Because your theta touches the vertical axis here. So make sure, once again, you apply geometry correctly. All right, other than that, I'm just going to plug it in. What is my force? My force that's going to cause this stuff to, or this rod to accelerate, is the weight of the rod, which is F of g. Well, how far is it placed? And from the axis rotation relative to the moment of arm, is just L over 2 sine theta. Well, my moment of inertia here, because the rod is pivoted at the end, its moment of inertia is 1/3 ml squared. And then I'm just going to keep alpha as is, because you're trying to find alpha ultimately. So, all right, and then I'm just going to expand F of g into M times g. So as you can see here, there are common terms on both sides. So I'm just going to clean up a little bit. I see an M there. I see an M there. I'm going to cancel that out. There's an L, and then there's an L square. So I'm going to cancel the exponent out. Yeah, make sure you cancel correctly, okay? And you just cancel the 2 out. Don't cross out the L. Other than that, you can just clean it up. The only thing left here on the left side is g sine theta over 2. And then on the right side, it's just 1/3 times L, or L over 3, however you want to write it. So I'm just going to go ahead and just clean it up. So it'll be G, L disappeared, that's just a 1. So it'll be 1/2 sine theta, and then L over 3 alpha. So to find alpha though, you would just multiply both sides by 3. At the same time, divide both sides by L. So that's going to look like this. It'll be 3 times G times 1 times sine of theta, which is just 3G sine theta. And then the 2 is in the denominator, but you're going to move the L on the top right to the bottom left, and that'll give it 2L. And that is going to match, let's see, choice D. Okay. All right. I hope that helps. Stay tuned. Don't be worried.